BYD Blade Battery, Toyota Solid-State Battery, 2027 EV battery tech, energy density, safety, cost, fast charging, and real-world lifespan. Everybody keeps framing this like a simple fight. BYD already has it, Toyota's promising the future. But the real engineering war isn't about who has the coolest chemistry. It's about who can build a battery that's safe, cheap, scalable, and predictable for normal owners at millions of units per year. Let's break this down. When I was turning wrenches, the pattern was always the same. The tech that wins isn't the tech that looks best on a slide. It's the tech that survives heat, abuse, and time without turning into a recall or a warranty disaster. So today, I'm going to translate what BYD's Blade Battery actually is, what Toyota actually means by solid state, what each one is trying to optimize, and what's realistically likely by 2027, based on where the engineering and manufacturing bottlenecks really are. First, we need to define the contestants properly, because most people are comparing the wrong things. BYD's Blade Battery isn't a new chemistry miracle. It's a packaging and safety strategy built on a proven chemistry, LFP, Lithium Iron Phosphate. Toyota's solid state isn't a product you can go buy today. It's a next-generation battery architecture, typically referring to a solid electrolyte instead of a liquid electrolyte, with the goal of unlocking higher energy density and faster charging while improving safety. Toyota has shown prototypes and published targets, and they've discussed production timelines publicly, but as of now, it's not a mass-market battery in customer cars. So this isn't battery versus battery. It's mass-produced, proven system versus high-upside system that's hard to manufacture. Now, what is BYD's Blade Battery mechanically? The Blade Battery is BYD taking LFP cells and making them long, thin blades, then integrating them in a cell-to-pack style approach. The key idea is reduce the amount of dead weight and dead volume between the cells. Traditional packs often have cells, modules, then pack. Blade style and other cell-to-pack approaches try to go cells to pack. Fewer modules, fewer housings, less structural overhead. And this matters because LFP has a known weakness, lower energy density than nickel-based chemistries like NMC or NCA. So BYD tries to win back some of that lost density not by changing the chemistry, but by packing it more efficiently and using structure smarter. Here's the part that made Blade famous: abuse tolerance. LFP is inherently more thermally stable than many nickel-rich chemistries. It's less prone to violent thermal runaway under certain failure modes. That doesn't mean it can't catch fire. It means it generally has a wider safety margin when something goes wrong. And BYD built a whole story around that margin, using tests like nail penetration and crush tests to demonstrate reduced thermal event severity compared to some other packs. But here's the nuance that engineers care about. Pack safety is chemistry plus design. Even a stable chemistry can be made dangerous with poor thermal management or poor mechanical protection. And even a higher energy chemistry can be made safer with excellent cooling and containment. BYD's Blade is basically a philosophy. We'll use a chemistry that's hard to panic, and we'll package it efficiently enough that the range is acceptable. Now, what is Toyota's solid state really? When Toyota talks solid state, they're usually talking about replacing the liquid electrolyte with a solid electrolyte. Toyota has discussed sulfide-based solid electrolytes publicly, and the big promise is higher energy density potential, because solid state can enable lithium metal anodes in some designs. Faster charging potential because of different ion transport behavior and the ability to handle higher currents if the interfaces cooperate. Improved safety potential because no flammable liquid electrolytes sloshing around. Toyota has also publicly stated aggressive targets in the past, things like long range and very fast charging times, often quoted around 10-minute charging for a big chunk of capacity. Treat those as targets under ideal conditions, not guarantees in a production car. Because the hard part of solid state isn't the headline, it's the interface. This is where it gets interesting. In a normal lithium-ion battery, the liquid electrolyte helps maintain contact between materials as they expand and contract during charging cycles. In solid state, you've got solid-on-solid interfaces, and solids don't self-heal contact the way liquids do. So you run into problems like interface resistance increasing over time, micro cracks forming, maintaining pressure across the stack to keep contact, lithium dendrite behavior still being a risk in some architectures if conditions are wrong, and manufacturing yield challenges, meaning you can make good cells in a lab, but mass producing them consistently is the boss fight. Now, let's compare what each side is actually optimizing for, because that tells you who wins what category. Category 1, Safety and Thermal Behavior. BYD Blade with LFP is already a strong baseline for safety. LFP's thermal stability is one of the reasons fleets and practical buyers like it. You can engineer safety into any pack, but starting with LFP is like starting with a calmer chemical personality. Solid state has safety potential because you're removing a flammable liquid component, but solid state doesn't automatically mean fireproof, and it doesn't automatically mean no thermal events. You still have high energy stored, you still have failure modes, and you still need pack-level containment and cooling. So near-term, real-world bet, BYD's Blade is a known safe direction at scale. Toyota's solid state is a high upside safety play, but the proof will be production reality, not theory. Category 2, Energy density and range. This is Toyota's main reason to fight this war. LFP is great, but it's not the king of energy density. So to get big range, you usually need a bigger pack, a more efficient car, or acceptance of lower range. Solid state's promise is higher energy density, especially if lithium metal anodes are part of the production design. Higher energy density means you can get more range at the same weight, or the same range at lower weight, or more cabin space because you need less pack volume. That can be a huge win for efficiency and performance. But again, promise versus production. By 2027, if Toyota can actually mass produce a solid-state pack with meaningfully higher energy density at an acceptable cost, that's a real shift. If they can't, then BYD's approach keeps winning by being good enough and cheap. Category 3, Cost and Raw Materials. This is where BYD is scary. LFP chemistry typically avoids nickel and cobalt. That matters because nickel and cobalt supply chains are expensive and politically messy. LFP tends to be cheaper per kilowatt hour, especially when manufactured at scale, and especially in regions with mature supply chains. BYD also vertically integrates more than most companies. They build cells, packs, and vehicles, so they can optimize cost across the whole system. Solid state, at least early production, will almost certainly be more expensive per kilowatt hour than mature LFP. New materials, new manufacturing steps, lower initial yields, and expensive quality control. So if your definition of win is cheapest safe battery that you can build in huge volume, Blade-style LFP is the current champion. Category 4, Charging Speed. This is the category everyone wants to believe will be solved by solid state. Here's the honest, up-to-date truth. Charging speed is not just battery chemistry, it's the entire system. It's cell internal resistance, thermal management, charger power, cable cooling, battery preconditioning, and the charging curve, meaning how long it can hold high power before tapering. LFP has a known downside. In cold weather, charging performance can suffer more, and you may see more aggressive tapering unless the pack is well heated and controlled. Many modern EVs handle this with preconditioning and thermal strategies, but physics still matters. Solid state has the potential for faster charging, but it has to prove it can do that repeatedly without degrading, and it has to do it safely across temperatures. So by 2027, the practical charging win might not be chemistry. It might be whoever has the best thermal management and software, because software decides whether the battery lives a happy life or gets stressed every day. Category 5, Lifespan and Degradation. LFP is known for strong cycle life. That's one reason it's so attractive for high-mileage, high-utilization vehicles. Solid state could be great for lifespan too, but again, the interface problem is the whole story. If interface resistance grows with cycles, you lose power and usable capacity. Toyota's job is to make solid state not only fast and dense, but durable over years of real charging habits. Now let's talk about the 2027 war specifically, what's likely to be true and what's likely to be hype. What's likely true by 2027? BYD will still be shipping huge volumes of Blade-style LFP packs, iterating pack structure and thermal management, and improving volumetric efficiency. LFP will keep getting incremental improvements, better low-temp performance, better packaging, better charge control, but it won't suddenly become nickel energy density. What might be true by 2027, Toyota may have limited solid-state deployment, pilot production, premium models, limited regions, limited volume if their manufacturing yield and durability targets are met. Toyota has discussed late-decade commercialization targets publicly. 2027 is often mentioned in media summaries, but the real timeline depends on getting mass production stable. What is not guaranteed by 2027? A full, global, high-volume Toyota solid-state rollout that replaces conventional lithium-ion across the lineup. That's a massive manufacturing transition, and Toyota is famously conservative about scaling tech before it's bulletproof. So the war is probably going to look like this. BYD wins volume, cost, and good enough safety and life. Toyota tries to win the premium tier, lighter packs, higher density, faster charging, if they can make the manufacturing work. Now, here's the key buyer-level takeaway that most people miss. This isn't just BYD versus Toyota, it's two philosophies of engineering maturity. BYD's Blade Battery is a production truth technology, proven at scale, built around a chemistry that behaves predictably, optimized for cost and safety. Toyota's solid state is a breakthrough pursuit technology. If it lands, it can change the rules on range, weight, and charging. But breakthroughs aren't free. They have to survive mass production, warranty reality, and 10 years of owners doing dumb things. And that brings us to the real conclusion. The 2027 engineering war won't be decided by who has the most futuristic chemistry. It'll be decided by who can ship millions of packs that stay safe, stay consistent, and stay profitable, while meeting what normal drivers actually need. Blade-style LFP is already winning today because it's predictable and scalable. Solid-state could beat it if Toyota can turn lab-level advantages into factory-level reality without pricing it into oblivion. Because in the real world, the king isn't the battery with the best claim. It's the battery that survives the most owners.